Alright, before you start going through this video, please try this example on your own because I'm going to just outline how to go through this example. So pause the video, go through it yourself, and then watch my video to check whether you've approached it correctly. So in this case, a 500-gram block on a spring is pulled a distance of 20 centimeters and is released. The subsequent oscillations are measured to have a period of 0.8 seconds. At what position or positions is the block speed 1 meters per second? So let's go ahead and highlight the things we know. We know the mass of the block. We know that it's pulled a distance of 20 centimeters and released. That means that's going to be the max amplitude that this block experiences. And then the oscillations are measured to have a period of 0.8 seconds. So we know what t is. So right away, we can go ahead and calculate the frequency of this oscillator by calculating 2 pi divided by the period, and we get that 7.85 radians per second. Now part A is at what position or positions is the speed 1 meters per second. So if we look at the physical situation, here's the equilibrium. This thing was pulled 20 centimeters and then let go and allowed to oscillate. So as this thing oscillates, there's going to be some distance somewhere away from this max amplitude, maybe somewhere around here, when it's headed inward, that it has a speed of 1 meters per second, and then it moves faster and faster and faster, moves the fastest here. Also, sorry, this image wasn't drawn very well. Technically, this thing should have enough room on either side to oscillate about its equilibrium. So here's the equilibrium position, 20 centimeters this way, 20 centimeters this way. So anyway, starts with 0 speed here. It speeds up, hits its maximum speed at this point, and then slows down until it comes to a stop, and then turns around and goes back. So that 1 meters per second is going to happen somewhere around here, and it's going to happen somewhere around here before it reaches its maximum compression. To figure that out, we're actually going to use the approach of conservation of energy, because this is a frictionless table that this thing is oscillating on. So conservation of energy tells us that the total energy at this point, when it's pulled to max extension, basically when this spring is pulled as far as we're going to pull it, which is 20 centimeters, the energy at that point, which is all spring potential because the mass is not moving, is equal to the energy at another point somewhere in between here where it's moving with some velocity v and it has some displacement x. So we set up the equation by doing 1/2 kx squared, 1/2 mv squared, and just to make this clear, let's draw that situation in purple. So when the block is somewhere here at a distance x away from the equilibrium, it has some velocity v at that point. So its total energy is some spring potential and some kinetic energy. And we want to find that position such that the speed is 1 meters per second. So we know the amplitude. Basically from here it's algebra. We know what the amplitude of this block is. It's 20 centimeters. We know what the velocity needs to be, and we know what the mass is. And since we know omega, we can basically, instead of plugging in a k, we can, so omega is root k over m. So if I can get k over m in my equation rather than just k, we know that's equal to omega squared. So I can use omega to plug in for k. Alternatively, you can use omega, you can use omega and you can use mass to directly solve for k if you prefer doing that. So I've shown my algebra by basically converting my ratio of m over k to an omega. And then you go through the algebra and you should get that the position is plus or minus 0.15 meters. That means when you are 15 centimeters to the right here or 15 centimeters to the left here, the speed is going to be this, which makes sense because we determined from our energy analysis that it's going to be somewhere between the maximum maximum extension to the equilibrium position, so somewhere around here. Okay, then part B says, what is the spring constant? Well, now you can just go ahead and use your equation t equals 2 pi times root m over k, or you can make use of the omega that you calculated to solve for k. And you should check your answer and get that it is 31 units per meter.